Okay, so before we kick off our discussion on cold flow, I'd just like to welcome our returning panel of experts. We have Andy Reid, our engineering manager.
Hello, everyone.
And we have Matt Ogden, our senior technical product specialist.
Hello.
All right, so let's kick off with an easy question. Matt, if you want to start with, what is cold flow?
Absolutely. Controversial subject. Okay, so I'm just going to share my screen. Okay, so this is two statements that I've kind of taken from one being kind of a scientific description of what it is, and the other one is taken directly from the standards. So the first one is cold flow is the viscous flow of a solid material at ordinary temperatures. It is the distortion of a solid under sustained pressure, especially with the accompanying inability to return to its original dimensions when the pressure is removed. So essentially that's saying that obviously if pressure is applied to something like a cable, that when the pressure is removed, it will not come back to its original state. Essentially that's something that we call, what's the word? Compression set is what I'm trying to get to. Yeah, exactly. So compression set is something where it will possibly flow back to its original state and its original dimensions. Now, if we take the wording from 60079-14, 10.2, this is really the only part of the standards where cold flow is mentioned. And it basically states that cold flow cables employ material which could exhibit cold flow characteristics. Cold flowing cables can be described as a movement of the cable sheath under a compressive force that's created by the displacement of a seal in cable glands, where the compressive force applied by the seal is greater than the resistance of the cable sheath. Cold flow could give rise to reduction in installation resistance of the cable. Low smoke and or fire resistance cables usually exhibit signs of cold flow characteristics. Okay, so essentially, so what's that saying is when a seal, such as something in our 501421 or our 501453 RAC, or even our 501453 universal, our diaphragm seal, that is obviously applying a force to the potential inner sheath of a cable that could cause potential issues. Now, the varying factor is always going to be the cable. We know how much pressure needs to be applied with the cable seal. The cables change, and obviously dependent on the selection of the cables will determine whether cold flow could be an issue. Now also the rating of that cable obviously could be an issue as well with regards to the fire resistant, flame retardant properties. And what we found is anything that kind of really has anything that conforms to 60331 or 60332 have these particular characteristics that cause the inner sheath to be almost like a cold chewing gum, an old chewing gum. And this is taken directly from a cable that is certified to that standard. And you can see that I'm just pulling the inner sheath away and it rips like chewing gum. The resistance of that material obviously is quite low. Now you apply something to that sheath that's going to obviously apply pressure, and that pressure needs to be withstood by the inner sheath itself. And if it is greater, then you will get deformation of the cable inner sheath and obviously potentially cause something called cold flow. Now, not all cables are susceptible to it. Sometimes the inner sheath is made of a much harder material and you can't pull this apart like chewing gum as I've shown, in which case, you know, a standard compression seal would be suitable, absolutely. But what we're trying to show today is what we have and what the ability that we've got with some of the seal designs, that we do have a solution without going down the route of a potential barrier gland. Now, to show this, I'm going to essentially make off a cable gland. I'm going to make off this compression seal. This is the same seal that we use on our 501453 RAC, essentially an equivalent to an E1FW. I'm going to tighten this as per the assembly instructions, which is tighten until you feel resistance, which is around there because the cable is quite big for the cable gland. It still moves, but the resistance is felt. And I'm going to apply one further full turn. And then at the end of the presentation, we're going to remove that to see what it has done to the actual cable inner sheath itself. So another half turn. And then also for continuity, I'm also going to put on the diaphragm seal. This is an A-size diaphragm seal. I'm just going to place that on the inner sheath This is a passive seal. It doesn't require any mechanical compression to activate it. So we call it a passive seal. It sits in place from the moment it's applied to the cable. So that is now sat in position on the cable in a sheath, and we'll remove that at the end of the presentation as well. And obviously all the questions that we're obviously going to be covering will be going into a little bit more depth as to what I've just discussed.
Perfect. Very exciting. Okay, well, moving on to our next question. We talked a little bit about what cold flow is, but how can cold flow affect the safety of cable installations?
The thing to bear in mind here is the cable going to try and move away from the compressive force of the seal, and what is the job that the seal is trying to do? Obviously, it depends on your protection concepts. Have you got an ingress protection seal compressing on the cable, or is it a EXD gas and flame propagation seal? So your risk is that the effectiveness of that seal is going to be compromised in some way, which could potentially have implications on the protection method of the gland, how well it's going to perform. For example, if you've got a displacement seal on a very soft bedded cable, and that soft bedded cable is moving away from the seal, are you potentially going to lose your explosion protection seal, and therefore there's a risk of propagation past the seal in a hazardous area? It's worth bearing in mind that the risks that we're talking about here could potentially be multiplied hundreds of thousands of times across every single cable gland that's installed on your site. So you have to consider, are you selecting appropriate glands for the cable types and the protection environments that you're installing into? You obviously want to take steps to limit risk as much as possible.
Yeah, I'd just like to add there that obviously the resistance of this material in this cable, obviously you have to apply a certain pressure to that. We obviously go about testing on stainless steel mandrels, as we've discussed in previous presentations. You apply a certain amount of pressure that is able to withstand a pressure test of 450 psi. Now, if you apply a pressure to a soft bedded material that has a low resistance, that is lower than the amount of pressure that's being applied, then that will slowly move away, which is reducing the pressure all the time. And by reducing the pressure, you're not then applying the correct pressure to withstand an internal explosion of 450 psi, which is obviously the phenomenon that we call cold flow. But the safety aspect of it is that potentially energy could escape underneath that seal between the cable and the seal that's obviously been tightened onto that cable. But because the pressure isn't there anymore, because the material flows away, energy could potentially escape underneath the seal, in between the seal and the inner sheath, and obviously escape into the wider world.
There's probably some other risks there to be aware of as well, because if you're displacing the inner sheath, moving the material around, are you going to risk potential damage to the conductors inside? Are you going to affect the resistance of the cable through that point? So a few electrical things to be aware of there as well.
Definitely, and we've seen issues where this type of cable that's certified to this flame retardant, fire resistant standards, where it's gone straight through to or over time it's moved all of this material away, and it's now then in contact with the conductors, obviously losing the installation resistance. And obviously, as per the standard, it states that could be a potential issue that needs to be obviously handled in the right way.
Absolutely. If you've just joined, if you'd just like to switch your camera off and turn yourself on mute. Okay. Moving back to the questions, unless either of you have anything that you'd like to add there. Matt, before you picked up kind of briefly on the difference between cold flow and compression set, but could you expand on that a little bit more?
Yeah, certainly. So cold flow is where, as described in that initial slide, where the solid moves away and it doesn't have the ability to come back. So it doesn't reform back into its original state. Compression set is something that materials go through where obviously over a sustained period of pressure that's applied to it, it can then have the ability, once you release that pressure to then reform and the material falls back into its original state. Now, one thing to remember is these cable glands are put under pressure for 25 plus years. You want to apply this pressure to maintain that protection concept that you're trying to achieve for 25 plus years in some instances, in which case you're not letting the cable flow back into its original state at any point. Obviously, you have regular inspections, and essentially maybe every 3 years you're doing a detailed inspection where you're undoing your cable glands and you're inspecting everything. That might be for 24 hours, could be a week, could be 2 weeks, but you're going to then reapply that cable gland and you're going to reapply the seal to that cable, which means that it's going to then reapply to that sustained point, and that's then going to continue to have the pressure applied, which obviously over the course of its lifespan will eventually cause problems. And it's about mitigating them circumstances. Essentially, we're not saying that our universal seal will not leave an impression. We're not saying that at all. It's about reducing the effects of cold flow. It has to have a pressure that's applied to the seal, but it's about the amount of pressure. And this universal seal, if you want to look at down the route of a seal on the inner sheath, we can control that amount of pressure by design rather than by installation. And that's what compression seals obviously have against them, is the fact that it has to be manhandled. It has to be compressed using a compressive force, a set of spanners, and it's only as good as the installer.
Mm-hmm. So we do actually have a question in the chat related to that. Hawke is using the compression seal on the outer sheath of the cable. How can cold flow be avoided by this compression seal? Now you've kind of just covered that, but if you wanted to expand on that point a little bit more.
So you're saying go on, Andy. You can put that one up.
Yeah, I can expand on that. What you have to bear in mind is the requirements of 6079-14, which basically state that if you're using a compression seal, the amount of force applied by the seal is required to be less than the amount of force it takes to displace the surface of the cable. By and large, the outer sheaths of cables are going to be pretty hard. Cables have to pass a load of testing, impact style testing, and it's unlikely that you're going to get an outer sheath of a cable that is susceptible to the effects of cold flow when using displacement seals. I think it's worth saying that Hawke's design of backnut seal is different to a lot of standard compression seals, where it's actually a plastic cage with a silicon sleeve, which does impart less force onto the cables if it's correctly installed. But I think when you're talking about the effects of cold flow and where you need to be really aware of it, you need to be looking predominantly at the inner sheath of the cable.
I'd like to expand on that a little bit. Obviously, the outer sheath, I've seen in instances on site where there is an impression in the outer sheath, and people have asked, is this a problem? Well, yes, it is, but you've got to think on how these things are designed. They're not designed to be swung off with a spanner. You tighten them enough to ensure that and if it's on an outer sheath of the cable, then potentially this type of design, yes, you would get EXD and your IP seal from a single seal. And the correct amount of tightness obviously ensures both of them. In some instances, we've seen cable glands where they're tightened to its absolute maximum. And if it does get tightened to its absolute maximum, that's just increasing the force, and whatever it's sealing against, obviously it always has a certain amount of resistance. And if you go above that, then you're going to get an impression. And as Andy said, obviously the design of outer sheath of cables obviously have to withstand mechanical impacts and other obviously design criteria. So they are generally harder. But a correctly installed cable gland to the assembly instructions that the cable gland manufacturer should give you should ensure that doesn't happen. But if you over tighten them, and this always goes back to competency and all of that, complex courses and being an understanding what you're actually doing as a fundamental exercise of installing a cable gland, that's kind of key to ensuring that doesn't happen.
Mm-hmm. So in the chat, Eduardo has asked, based on the IEC 60079-14 standard, can we consider that cold flow is critical mainly for EXDB protection? In
the world of dual certified cable glands, obviously we have dual certified cable glands, and most other cable gland manufacturers also do. Cables can be specified for, cables such as these can be specified for EXE applications. Now, although that inner seal isn't required for the protection concept it's going into, because obviously it's EXE, this is essentially a flame-proof seal, which gives you EXD protection, then no. But if you install it and you over-tighten that inner seal, then you could have things like low IR readings, obviously damaging of the cable, things that could potentially, you could potentially cut through that material, that the inner sheath material that much that you could get cross wires between the cores themselves. You know, we've seen exposed cores on some testing that's taken place. So I would say it's a yes or no answer. You don't essentially need to have that inner seal in place, but in the world of dual certified cable glands, that's part of the installation and has to be in place. So it does have to be managed in such a way where you're not causing damage to the cable that may cause other issues other than a potential flame-proof issue.
Perfect, thank you. And Andy, anything you'd like to add there?
No, I'll probably agree with Matt, where you do have to be aware of your protection concepts and the actual design of the gland and how it's been installed if it's dual marked. But as Matt mentioned earlier, you know, we have seen issues where glands have been incorrectly installed and over tightened, which can then affect the ingress protection capability of the product, which as a knock-on effect can affect your EXE protection. So I think it's probably mainly with the soft inner bedded cable in mind and D-seals on that, but you know, you should be aware of all aspects of installation.
Perfect, thank you. Well, there's quite a few questions coming in about the -14 standards, but before we kind of go back to that, because there was a question submitted via the form, obviously, about that as well, I just wanted to touch back on cables again and talk about the cable types that are affected by cold flow. Now, we did have a question about whether it affects armoured or unarmoured cables specifically.
Yeah, with armoured or unarmoured, the actual armouring of the cable gland doesn't affect how susceptible it is to the effects of cold flow. Having said that, an unarmoured cable will normally be quite hard because it has had to pass cable testing, cable impact testing, etc. And more often than not, we see very soft inner sheaths on the fire-resistant type cables, which do have some armouring within them. But if a cable is stated armoured or unarmoured, that's not really a strong indication on its ability to resist the effects of cold flow.
We try and always ask for a cable data sheet where possible. Obviously, it gives us sizing and ensures we spec a cable gland that's suitable for that particular cable itself. And within there, obviously, it'll tell us the standards that it's designed to and the standards that it's passed. So we can make an assumption from that. You know, a piece of sample cable is obviously the best. And then it's kind of looking at what you can potentially do on site to try and learn to understand what the cable construction is and whether this is potentially an issue. And, you know, this cable inner sheath is only there in specific types of cable. And this particular cable is a BFOU cable. We see it in RFOU cables, in RFCU cables. And it's not a problem on every single cable. We're definitely not saying that every installation should have a universal cable gland on it so you can seal on an inner sheath where we feel that we can manage the compression. Absolutely not, because we have the other cable glands and we sell millions of them every year. So we want to just kind of put it out there that we're not saying that this is the only option, but you have to be aware of what the cable construction is to understand whether you need one. You know, we have a very strong history of coming up with solutions, and I think by design we're able to do that, and we have some very talented designers. And you know, this was something that we brought to market 20 plus years ago, and it's still stopping this issue now. People still spec and live and die by this seal, and we have to we can't obviously, ignore obviously the other cables that are in the marketplace, and the 51453 RAC that uses compression seals still absolutely has a place. So yeah, just ensuring that you know what the cable is and the characteristics of that cable by looking and taking a sample of it and analysing it and even putting a 501421, just a simple compression gland on it to see what it does to that inner sheath would be a good indication as to whether it's going to be susceptible or not.
Perfect, thank you. Well, like I said, we'll get to some of those questions about the standards in a second, but I'm just going to read out a couple of questions that we've had. So Dave has said, cold flow cables are they mainly, oh gosh, quite a few coming through here. Cold flow cables are mainly susceptible to offshore, i.e. RFOU and BFOU cables.
I think that's probably the case in most instances. Onshore cables, from my experience, are a little bit harder. They use a different material on the inner sheath, but that doesn't mean they're not specified. So yeah, you could probably as a generalization, you could probably say that, but again, it's understanding what the characteristics of the cable, the way it's made, manufactured, extruded. Is it extruded using a very soft inner sheath? Is it designed to 331 and 332 that could have and cause the material to be soft and get softer even with temperature, and understanding the operating temperature of the installation and whether heat is a factor too.
Anything you'd like to add there, Andy?
No, I think Matt's covered that in a nutshell for sure.
Okay, perfect. So this is another question from Estelito. It seems that the problem rises when someone dismantles cable glands. Have you got test reports of the propagation test, EXD, made on cable glands installed for some month, but with no dismantling actions? If the cable adapts against tightening pressure, it seems that the IP and EXD integrity is kept, isn't it?
Do you want to pick that one up, or do you want me to?
Yeah, so there has been some independent testing of Hawke cable glands on cable to ensure that the propagation protection is maintained. One kind of feature of the diaphragm seal is if there is any movement of the cable underneath the seal, which is generally going to be less, if at all, compared to a displacement seal, because there's less force imparted on the surface of the cable. The diaphragm does have the ability to move with the cable itself. So we have seen testing in the past performed independently that has proven that this type of cable gland will maintain the propagation protection over time.
I think going back to a previous point that I made was regarding the resistance of the material and the pressure applied. You have to maintain a certain pressure to withstand an explosion internally, and if that pressure is reduced, and by the fact that the material is moving away, that pressure is reduced. And over time, I don't know whether we've done any testing on cable glands where we know the cable is susceptible to cold flow, and we've applied an amount of pressure to it, and we've not retightened it, and we've applied pressure to it. I'm not sure. We'd have to have a look back in some test reports to see whether that's a test that we've done, but it may be something that's we would be interested in looking at, without doubt. So yeah, I think by undoing them can again cause further issues, but I think that you would get a transmission between the cable and the inner sheath as the material flows away. But again, I haven't got any test material to back that up with me today, but I will certainly have a look at that. I think one other point to mention actually is it's not just about maintaining your EXD flame-proof requirement. It's about inspection. It's about maintainability. It's about all them things that go into the design of a product that ensures it will last the test of time. You don't just put it into commission, you leave it for 25 years. You have to come back to it. You have to ensure that it stays in the correctly installed state. So by design, or by installation requirements, you have to take these things apart periodically, which obviously could have further impact on these issues.
Okay, great. Well, there's a couple of questions actually coming through about inspection, but before we go to that, let's go back to kind of the standards and let's talk about how cold flow is measured and the test for it first, and then we'll go on to that -14 standard a little bit. So if you'd want to talk a little bit about the test for cold flow.
Yeah, so as far as I'm aware, there is no defined test for cold flow. Therefore, we find it difficult to see how we can state compliance with a test that basically doesn't exist. All that the 60079-14 standard says is that A, the force of your seal can be no greater than the amount of force it takes to displace the surface of the cable. And basically that you have to choose cable glands that are appropriate for installation. So it's not actually called out as a specific test within the standards themselves, although it is something, we do put glands on cables to define suitability when required. But it's not actually specifically called out as a test that has to be performed and passed within the ATEX standards.
So how is it controlled then?
I think the only control is that the installer has to ensure that they're choosing cable glands that are suitable for the application that they're going into. And obviously we will advise wherever we can to try and ensure that those selections are correct. But it's basically controlled through the correct installation of the product and the maintenance and inspection schedules thereafter.
Okay. Perfect. If you've just joined, if you want to just mute yourself, that would be great. So if we want to talk a little bit more about that -14 standard in a little bit more depth there, we've already established that it's not an explicit test, and we've said it's kind of, in the hands of the installer to a certain extent, but we have received a few questions about that standard. So if you want to expand on that a little bit.
I mean, -14 is obviously the installation standard, and it refers to methods of installation to mitigate circumstances and to ensure that you can have a product that will stand the test of time and obviously live for as long as you need it to. And -14 is all really about having somebody who is familiar with these products, competent in what they do, ensuring that they install correctly, and that's a set of guidelines around that installation process for whatever it is for products that are certified to a specific protection concept. So yeah, it covers a lot of different scenarios. Cable glands are a very small part of that, obviously, with blanking elements, enclosures, all of them things that these things have to interface with. Obviously, it's about making sure that they've got a set of rules to govern the way that they install these products and to ensure that they meet the requirements throughout the lifespan of the products, whether that be cable glands or enclosures or motors or whatever it may be.
Perfect. Well, kind of going back to that standard specifically talks about, like you say, ways to reduce. But Dave has asked, are there any ways to eliminate cold flow?
The best way, go on, Andy, you can pick that one up. I think we're going to give the same answer anyway.
If you've got a seal on the inner sheath of a cable, there's always an element of force on the cable itself. If you were to install a barrier type gland, that doesn't impart any force onto the inner sheath of the cable, as it forms seals around the cores. So you could make an argument that a barrier gland is really the only type of gland that could eliminate cold flow on the inner sheath of the cable because it doesn't impart any force onto the surface. However, you're not going to want to install that type of gland in every single application, as it's cost prohibitive, much more expensive to install, takes more time, more expensive to buy. So you need to review your application, review the type of cable that your gland's been installed onto, review your type of protection concept, and choose the appropriate gland for the installation.
And
was that the answer you were going to say, Matt?
Pretty much. That's essentially all set out in -14. And I'd like to touch base on a design feature that we've obviously put into our new range of glands that we launched in 2019, was the fact that you can upgrade it. So essentially all of them things that Andy's just mentioned needs to be managed, and really that's managed by the installer to ensure that they've got a suitable product for the installation that they're currently working on. Now, if they find that the cable that they've got is going into whatever it may be going into, and they don't deem that to be suitable, and they feel that a barrier gland would be better, then you can just upgrade the cable gland that you've got by purchasing an upgrade kit, which means you use the same body. We use the same four out of the 5 components are the same, and you purchase that upgrade kit that can change it from a universal gland, which is this type of seal, to a traditional barrier gland, which is a liquid pore seal, or a putty type seal, depending on the installation requirements, which is obviously something that we wanted to include within our design upgrade of our glands last year, just to make them more versatile on site, because these are issues that people are facing day to day in the field.
Okay, perfect. And just, you've mentioned barrier glands, you've mentioned, kind of that in every case, the types of cable should be evaluated that people are using. But what would you recommend as generally the best type of cable glands for protection against cold flow?
I think we have.
Oh, go on, Matt.
Sorry, I think we have to go on our testing longevity. This design has been around for a long time and has worked in a vast amount, many thousands, millions of applications. There are environmental issues where things could potentially go wrong, and I know there's a lot of pictures that don't necessarily tell the right story online and things, and we need to obviously face up to that. And things that, like environmental issues, could mean that this doesn't have the effect that it's designed to have. And if that's the case, then fair enough. We understand that obviously that could cause issues, but in the vast majority, and I'm talking like 99.999% of all applications, it does, and that's what it was designed to do. Now, obviously, the cable gland with this seal over a barrier gland is pretty much half the price, and to say that you're just going to, for one issue that could have occurred, just to switch to barrier glands and it costs you hundreds of thousands and more pounds on a big project, I think is a bit extreme, when there's a perfectly good design that we feel doesn't cause, and we can manage that amount of pressure that's being applied to the cable itself. We've had a lot of history with this particular seal design. We've had a lot of people try to copy it and have been unsuccessful, and as far as we're aware, there isn't any other cable gland that has the same effect as this particular seal design that we have, which is our diaphragm seal.
I mean, the key thing to remember about that seal is it takes the installer out of the equation when it comes to tightening up the seal onto the cable. With displacement seals, it's so easy to over tighten them, particularly onto soft bedded cable. As you tighten up the universal seal, it doesn't impart more force onto the cable. It's passive. And also you can see it when you undo it. You can undo it and pull it out and it's still in contact with the cable, so you can see what's going on. With a displacement seal, you undo it and the displacement seal loses contact with the surface of the cable, so you can't inspect it in situ in the same way that you can with the universal.
Once it's slid onto the cable, that is where it sits for the remainder of its days, and you can inspect and ensure that that is in good working order without uncompressing anything. It's in position for the whole amount of time of the product's life.
Perfect. Well, we'll kind of go back to inspection in a second. Before we do, we've just had another question which relates to the kind of the topic that we were talking about the best glands. Estelito has said, we find a lot of cold flow cable glands in the market. How can the customer really know which ones are functional, proven, and which ones are, he said, the fake ones?
Well, I mean, it goes without saying, Hawke's got 20 years in the market with this type of seal. So it's proven basically through application and through being installed, and we can demonstrate our success in that way. I'd be very wary of getting statements from the manufacturers on cold flow compliance, because as we've talked about before, what are you stating compliance to? Because there's no real test or standard that you have to adhere to. And B, particularly if it's displacement type seals, they're putting it on the installer, the end user, which is you guys, to tighten up the gland correctly. And if you overdo it and throttle the cable, that's the issue's not with the manufacturer. So I just think you have to be very careful of just taking statements. I think you have to understand what the situation is. You have to understand your cables and your application, and understand the glands, understand the pros and cons of different glands and how they work. And I think the best way you can make a decision is through education and through coming on calls like this where we explain what's going on.
Definitely. Anything you'd like to add there, Matt?
Not for me.
No. Well, let's just kind of consolidate that. So Tunmin has asked, so can we say the ICG 653 is the best, followed by the 501453 universal for the cold flow issue?
If you're just, I was going to say, if you're just saying cold flow and nothing else, then yes. But you have to consider costs, you have to consider installation time, you have to consider your application, and you have to make a judgment after looking at those things. You know, consider your type of cable. But if you want to say just to eliminate cold flow, then there is an argument to say the ICG is the gland that does the best job of mitigating that. But as Matt's already said, in 99.9% of applications, the universal is an appropriate choice also.
If the cable meets the standard, certainly for EXD, you know, there's obviously a lot of things to discuss regarding protection concepts that we've gone over before. You know, it has to be greater than 3 meters, has to be extruded, compact, circular, all them things. So if that's the case, then, like I say, you know, cost and effectiveness on the cable needs to be looked at and considered.
Perfect. Thank you. Right, so I want to make sure you've got time for the kind of grand reveal of the experiment. So I'm just going to go through a couple more of these questions on here. So Adam has said, you correctly mentioned that the ongoing detail inspections require dismantling of the gland. It is when these further detailed inspections take place that cold flow is normally noticed. When reinstating the gland after this periodic inspection, how can you guarantee that the gas seal when it's reinstated? Are there any limits to the deformation that once the deformation exceeds a certain amount, the gas seal may be impaired and therefore the cable should be replaced?
Yeah, I think well, there have been cases where the level of cold flow that you see is so much that it does take the diameter of the cable below the lower limit of the gland. So by the very fact that your diameter is out of spec, that's potentially an unsafe situation.
That's what I was just going to say. Yeah, you're deforming the cable, and if the cable allows for the seal to be released, because this is another subject that we could talk about is thermoplastic versus thermoset materials. If you can actually get it off to inspect it, then if you reseal onto that, you've got to take into account that's then your inner diameter of the cable. That obviously has to be within a certain range for that seal to be effective to meet the certification requirements of the equipment that you're installing onto.
But again, that's a plus point of the 51453 universal, is you don't have to disengage the seal to do detailed inspection.
Exactly.
Which brings, Christopher has asked, when doing a detailed inspection, you are supposed to take a gland report. I've always been told that once you take a gland apart, you're supposed to install a new one. How does this work?
I think reinstalling old cable glands onto new cable is frowned upon, but if you are taking a cable gland apart for inspection purposes, then you're just reinstalling it in the same position. I think that's obviously deemed acceptable. Now, that's down to site requirements essentially. It's not for us to say that whether that's right or wrong. But we would, if someone was to come to us and say we want to install some old glands on a new piece of cable, then that would be slightly different as to, well, why have you removed them in the first place? You know, we don't know what them factors are to say whether them cable glands are still fit for purpose.
Mm-hmm. Okay, and just kind of going back, how can you check for cold flow issues when glands are installed?
So the only way you're going to be able to do that is by doing a detailed inspection and exposing the areas that are being sealed. Obviously, with the Hawke cable glands, as we've said a couple of times, you can install the seal in situ on the cable. With a displacement type seal, the only way you're going to be able to check for the effects is undo the seal and expose the surface of the cable to see what's going on.
I'll do some kind of test like this for a number of hours, days, weeks, if you can. You know, that will show the exact same process, and over time it'll just exacerbate. And as the temperatures go up and down and fluctuate over the seasons of the year, and all of them things need to be considered. So, yeah, by doing a simple cable test, you'll be able to see whether it's going to potentially cause issues, and you're able to make a judgment from that.
Perfect. Well, we have got a few more questions, but I'm conscious that it is time now. So, Matt, if you'd like to kind of reveal the experiment, and those of you that have asked extra questions, we can either stay on for a couple of minutes after this, or we'll make sure that we get back to you separately
Okay.
if you have to jump off.
No worries. So remember, I put one turn onto this cable gland, and that's as per the assembly instructions to ensure that we meet on a stainless steel mandrel pressure tests. So I'll just undo that, and we'll see what it's done to that cable in a sheath. And there's, so I don't know if everybody can see that. It's basically there.
Mm-hmm.
So you can see that's probably changed the inner seal by the inner diameter by 2 mil, a mil either side, I would say. And over time, that's just going to continue to get worse. Now, if I left that for 24 hours, it would probably come back somewhat. And I have done some other tests on other cables, and that was one that I did yesterday. I don't know whether you can see that. It was much worse yesterday, but you don't have time for that cable to come back. You need to obviously recommission that and put it back into service. So at that point, you're just going to continue to apply pressure at that particular point, which is obviously going to continue to change the shape and cause a deeper divot in that material itself.
Matt, can you just put a white piece of paper? Have you got a piece of paper to hand that you could put behind that cable?
No, I haven't. Let me just see.
Joy of life.
There we go. Right, okay. So is that better? Can you see that? Yeah?
Yeah, that's good. Perfect. Thank you.
So I'm going to remove the universal seal's been on the exact same amount of time. I'm just going to move that out of the way, pull that off this end of the cable, and then again we'll use a. There is literally nothing that's been applied. No, there's no imprint of that seal in any way. Everything is still in shape, and obviously not caused any damage at all. So, you know, that's only a 30-minute test, and that's done something like that. And this is our, like I say, traditional kind of compression seal. And again, I'm not trying to say that to shy away from these particular cable glands or the 501453 RAC, absolutely not. But it has to be determined for whether it's fit for purpose by the cable type, which is obviously the moving target, if you like. That's the thing that's ever changing, is cable specifications. And by doing a simple test like we've just shown, that kind of, you'll be able to get an understanding as to how the cable will function and respond to a typical compression seal, mechanical compression seal, that's like this particular type of cable gland that we have.
Okay, perfect. Well, thank you for that, and thank you to everyone that's joined this call. If you want to jump off now, please, absolutely feel free to. This has been recorded, so we're just going to cover two more, if that's all right with you guys, of the questions that have come in. And then we'll stop, and any other questions that we haven't responded to, we'll make sure they're responded to individually. So I've got a question here from Sven. Allowing for the universal seal being stretched in position, does a fluctuation in the temperature affect the performance and long-time tensile performance? And potentially, what is the life of a universal seal? So quite a few questions there. Let me know if you want me to repeat that one.
So it's worth saying that this type of seal has been tested and certified in accordance with the standards. And part of that testing is thermal aging of the product in order to define its maximum and minimum operating temperatures. So those thermal aging testing is generally considered to be around 20 years or so through installed on a product at its limit of service temperature. So my general answer would be, it's very dependent on application, how aggressive is your environment, are there any chemicals or vapors present that could have detrimental effects? But generally speaking, it has been tested to around 20 years of its life.
Perfect. Anything you'd like to add to that one, Matt?
No, there's obviously set out in the standards as to what we need to test to, and determined by the operating temperature that we want to put on the product determines the high temperature that we and the low temperature that we have to test at. So yeah, obviously the thermal aging cycle obviously puts all of these plastic and rubber components to its absolute limits and mimics a 20-year lifespan. Yeah, simple as.
Okay. Well, the next question is from Eduardo. So as we're talking about the cable too, should we perform the test as per Annex C to ensure the safe use of cable for EXDB protection? I'll leave it as that. He does say that he's not seen manufacturing form on their data sheet that the cable is enabled for that application. But yeah, I'll let you carry on.
Now, that's something that I think we covered on one of the other seminars as well. I would always say use the 9.3.2 criteria with caution, because you're relying on the performance of your cable to prevent a propagation at the center of the cable. The Annex C test is an indicative test, and simply that to see if your cable will prevent propagation in an explosion situation. The key thing here is how are you controlling that through the manufacturer and the cable you're actually using on site. No one's doing periodic testing of cable to Annex C. So if you're relying on that to avoid using a barrier gland in EXD, I'd just say use that with a word of caution, really.
Okay, perfect. Well, that seems like a good place to close up. For those of you, a huge thank you to everyone that submitted questions today, and thank you all for joining. Like I said, if we didn't get round to your question, we will make sure that we respond to it outside of this presentation as well, and we'll let you know when the next session will be as soon as we can. And we will also get the recording out to you within the next week as well. Thank you all for joining, and we'll see you soon. Bye.
Thank you.
Thank you.